So, Michael Stanley is a new postdoctoral researcher at NASA Langley Research Center, contracted through Analytical Mechanics Associates. He obtained his PhD in statistics from Carnegie Mellon University under Mikael Kuusela, with a thesis focused on statistical inference for ill-posed inverse problems of carbon flux uncertainty quantification, and was awarded a strategic university researcher partnership to develop decision theoretic and optimization based uncertainty quantification. This work centered around the strategic desire to provide prior free uncertainty quantification alternatives to NASA and remains a key focus of his research. More broadly, he is interested in the intersection of statistics, probability, optimization, and computation. And this morning, he'll be presenting a talk entitled Optimization-Based Uncertainty Quantification for Non-Destructive Evaluation.
Okay, thank you, Michael. Can everyone hear me okay? I'll take that as a yes. All right. Thank you for the introduction. As Michael said, my name is Mike Stanley. I'm a postdoctoral researcher stationed at NASA Langley, and I'm definitely coming from the stats world, so I'm still, I think, coming up to speed on what you guys are all doing here and kind of the engineering side of things. But I've been fortunate enough to get involved with this interesting problem in non-destructive evaluation and had the opportunity to apply and continue to extend some of the research and methodology I was working on during my PhD. So I'm excited to talk about that work today. Okay, so before I get to the actual methods, I like to think I'm an application-driven statistician, and I look to develop methodology based on particular applications. So the thing we'll be talking about today is inferring properties of bonding composites. And I'm going to switch to this microphone because I feel like I'm okay. Can everyone hear me okay? All right, perfect. Okay, so the problem we're addressing is inferring properties of bonding composites, and this problem really arises from this idea that next generation aircraft will increasingly rely upon bonding composite structure, and there's no widely adopted non-destructive evaluation, or NDE as I'll call it, method to evaluate bond strength. So the engineering objective that we are building upon is to investigate a swept frequency ultrasonic phase measurement technique for the ability to measure interfacial bond strength. And this idea and this approach is based on this particular paper from Haldren et al. In 2019. And I have a little schematic here which illustrates kind of the idea where you have two adherents which are bonded together by some sort of bonding material, and you send ultrasonic waves through adherent 1. They go through, some of them are reflected, a little bit more goes through, some are reflected, and then finally more go through. And so with this model, we can write down some equations, and I will refer to this for my purposes as the forward model. And this forward model is a function of some material properties, theta, and will also be a function of the input ultrasonic frequencies, which I'll refer to as omega. Now, the parameter vector of interest for us is this 5-dimensional vector. And the first parameter is actually the thing that we're most interested in. This is this interfacial stiffness. And then we have these other nuisance parameters that, I'm using some statistical lingo here just to say that some parameters that we don't care about reporting uncertainty on, but nonetheless need to take into account when reporting uncertainty on interfacial stiffness. So this is acoustic attenuation, some affine correction parameters, and bond line thickness. Another interesting wrinkle in this problem is, as you can see in our parameter vector, so this is not just a straightforward inference problem or inverse problem where we are looking to take some measurements and say something about interfacial stiffness. We're actually interested in bond strength, or tensile strength as it's called on this bottom plot. This is a plot again from this Haldren paper. And so there's this extra dimension of how can we go from interfacial stiffness to tensile strength or bond strength through an existing linear regression between those two variables. So on a high level, the UQ objective is to characterize the uncertainty in these inferences to bolster confidence in the proposed NDE procedure. And that's what we're going to talk about today. Okay, so now a bit of the statistics nerding. So we'll assume a constant variance additive noise model. And I've been assured from my scientific collaborators that this is reasonable, although of course we could posit a different model and think about different techniques. But kind of the characteristics of this is that we have this, again, deterministic nonlinear forward model, and we'll think about evaluating this at a fixed vector of ultrasonic frequencies. So now I'm using notation a bit. This omega is now a vector of length n. Critically, we also assume that our parameter vector, our true parameter theta star, is contained within this particular hyperrectangle. And although I just put up that image, I'll just mention that the noise term here, we're assuming that it's Gaussian and that it has constant variance. Again, you could relax this, but I'm not going to right now. So we'll also consider two different regimes, which I think will be illustrative of both kind of what you typically see. I'll call this the typical parameter setting, and then what I'm going to call the boundary model, which will help us tease out some of the importance of handling those nuisance parameters in the parameter vector. And to give you a sense of how this method performs under different noise assumptions, we'll also consider realizations of the data under several different noise regimes or values of sigma. And just to say a little bit more about these two different parameter settings we'll use. So in the typical setting, I'm thinking about this as all those parameters in that vector are away from the boundary. So away from the boundary, what we know to be physically realistic. And again, this demonstrates performance under typical circumstances. But to be methodologically rigorous, we of course want to know that our method has some sort of known properties under any possible theta, any possible parameter vector in that constraint set. So this boundary setting is one in which I set the acoustic attenuation to be very close to its boundary. So it's known kind of realistic settings. And this will, again, demonstrate the effect of nuisance parameters. Okay, so now I'll get into maybe the most controversial part of my talk, which is establishing a standard or a guarantee for this methodology. And I'm going to posit that coverage probability is a sensible UQ calibration metric. So the thinking here is that NDE techniques are typically repeated many times, and thus a frequentist guarantee on any UQ is sensible. And I'll explain more precisely what this means. We propose a procedure returning a set of plausible interfacial stiffness values, and therefore bond strength, from a realization of our assumed data generating process, such that the true interfacial stiffness is within the return set with some known probability or some fixed probability. And mathematically, we can say this precisely. We choose an alpha, and my job is to then come up with this confidence set procedure which maps our data to open sets in our real line for interfacial stiffness, such that if we do this thing a whole bunch of times, the probability that our set covers the true parameters value is at least 1 minus alpha. And again, the important thing is that this needs to hold for any possible theta star. And this is what I'll call a coverage guarantee. Okay, well, that all sounds, that's great. But what are some desirable features here? Of course, classical statistics is replete with procedures that purport to do this, at the very least asymptotically. But I'm going to add a few other characteristics that I think are relevant to physical problems. The first is that our confidence set should respect the known parameter constraints. This may sound trivial to folks who come from engineering, of course, your analysis should be realistic, physically realistic, but actually, in my experience, a lot of statistical methods, which are born out of different applications, do not necessarily respect this. So I'm going to want to control this procedure to have awareness of the constraints, both in in the construction natively and in the output set. So the set should only return values that are physically possible. And I'm also going to give us a way to distinguish between different confidence procedures. So for a fixed level, I'm going to say I prefer confidence procedure A over confidence procedure B if one is smaller on average than two. And this will be an important kind of metric, if you will, when I'm showing how our method performs against a baseline. And finally, as you can see from kind of the setting here, we're interested in developing methods that work natively with the so-called black box computational forward models. So, of course, this talk is about a particular NDE application, but I know you folks deal with a lot of different types of settings, and so if you have a setting that involves any sort of black box computational model, I'd like to suggest that maybe you can do something similar here. Okay, so as I mentioned in the intro, this work is an extension of some of the work I did during my PhD, which was largely about these optimization-based confidence intervals. And I think they provide a good starting point to a solution to our problem. So the entry point here is for inverse problem UQ with deterministic computational forward model and known parameter constraints. These methods, with some small citations on the bottom, provide a good starting point. And I think these are really intuitive and nice, mostly because I can draw a little schematic that describes what's going on here. But the idea is that we get our data Y, and that defines a set of, let's call them feasible parameter settings that could explain our data. And then if you give me a quantity of interest, this can be some linear functional of our parameters. It could be some other function entirely. The idea is that we simply minimize and maximize our quantity of interest over that feasible set, which again is a function of our data. So this is great because we can now basically port our uncertainty quantification task to optimization, which is computationally native. It's very well developed. So this has a lot of advantages. But the challenge is how we set some elements of that constraint set ahead of time such that the interval we get out results with a coverage guarantee. And this is the important part statistically. Okay, so there are a few known settings that work based on the assumptions that I provided. I'll call these the simultaneous strict bounds. The strict bounds word comes from some work Philip Stark did in the 90s, where he was developing statistical methodologies that, again, respected physical constraints of some geophysical problems he was working on. I'll come back to this if people have questions about it, but kind of the thing you should take away here is if we know the variance, we can use a chi-squared distribution or quantile in certain ways, calibrating either to the observation space or the parameter space. And we're going to extend this this framework to suit the assumptions of our problem. So the first step of doing that is defining our quantity of interest, which again, if you remember, our parameter vector is simply just plucking the interfacial stiffness value out. So our H vector here is just going to be a 1 in the first position and 0 everywhere else. Okay. So as I mentioned, we're extending this methodology, and there are some key innovations that we need to include. The first is my scientific colleagues have again assured me that they don't know the variance necessarily. No problem. Statistics deals with this all the time. We can apply kind of a traditional studentization type approach here and use F quantiles instead of chi-squared quantiles, and I'll explain how that works in a second. The second is all the work I did previously assumed a linear forward model. And as I mentioned at the start, this is a nonlinear setting. So it's not obvious that any coverage guarantee or any computational methods that we're using would also work well in the nonlinear setting. The way we handle this is proposing a two-stage procedure, which basically amounts to a linearization step followed by assuming the model's linear and proceeding as normal. The third thing is, again, this propagation step of taking an interval we acquire for interfacial stiffness and using an existing linear regression to put that into bond strength. And kind of a key thing here is we want to do this in such a way to maintain the coverage guarantee. Or to think about it differently, we want the target, the coverage guarantee to be on the bond strength, but that's not the confidence set we're initially getting. So there's a little bit to do there, and we have a procedure to do that. Okay, and so I structured this a little differently here. Now the overview of the rest of the talk, now that we've gotten the intro out of the way, is I'll first talk briefly about this propagation. Although we're still in the simulation phase, so I don't have real data and therefore cannot show kind of real results for that first step. I did want to describe the approach and the mathematical details, so you could go, play around with them if you wanted. But the meat of the talk here, the rest of the talk, is first describing this two-step procedure. And then I'll go into some empirical results, some simulation results on computing those interfacial stiffness intervals to demonstrate our method's ability to basically outperform what I'm going to call the baseline comparison. And this, again, will be on these two parameter settings. Okay, so just to briefly talk about how this interval propagation idea works. We're starting with another data generating process. So this comes actually right from the Haldren et al. Paper. They posited, and I think empirically kind of verified, that a linear assumption is not bad when regressing bond strength onto interfacial stiffness. So we're going to proceed as using that assumption. And now we can pretty heavily just rely on classical statistics and say, well, if this linear assumption is true and we're Gaussian and all that, we can very easily construct simultaneous confidence sets such that for any x, our confidence band has the right coverage level across all x. And the intuition I'm going to suggest here is that if we have such a band, which I've indicated by this kind of orange band, and we have our interfacial stiffness interval on the x-axis, we can simply minimize and maximize the value in our band over that interfacial stiffness interval. And if we set the confidence levels of both the interfacial stiffness interval and the band in a strategic way, then the resulting bond strength interval will also have the desired coverage level. And again, I'm just kind of flashing this as a little advertisement, but we do have a little lemma here, and there's a proof to show how you can set these things. But for now, I'm going to move on. So to briefly describe this two-step approach to handling the nonlinearity. The first step is to do an intuitive thing, which is to obtain a least squares estimate, or in this case, actually, equivalently a maximum likelihood estimator. And then we linearize our forward model around it. And it turns out that in our case, the forward model is computationally pretty low stress, or has a low burden. So this is a pretty easy step to do. And then we're going to execute our SSB, our simultaneous strict bounds interval computation, modified, of course, to handle an unknown variance. And if you're familiar with the nonlinear regression literature, mostly from the 90s, again, we have some small references there. You'll know that this is actually a somewhat standard thing to do. But I'd like to point out that typically in that literature, the coverage guarantees on confidence sets and confidence intervals are asymptotic and require extensive knowledge of differential geometry, which seems very interesting. And maybe I'll get to that reading on my next vacation, but unfortunately I don't have that expertise. So I'd like to think that this procedure we have is going to circumvent some of those details. And since I'm have a bit less time than I was expecting, let me skate through some of these mathematical details. But here, I just like to point out that there's a kind of traditional way that we can account for the unknown variance. Again, this is kind of the studentization trick. But the challenge here is that if we directly use our forward model in the definition of this confidence set, then we inherit its nonlinearity, and optimization can become very difficult. So, to make our lives easy, we suggest that you get your least squares estimator, you linearize, and then you define this set, which again gives you a set of feasible theta parameter values, and that gives you your final interval. And now I've made our lives really nice and pleasant because this is now a quadratic program, and I have a bunch of solvers that I know can solve this really well. Okay, so just to briefly describe our baseline, we're going to use this least squares interval as a baseline. And this follows the somewhat traditional approach, I think, in statistics of obtaining an estimator and then somehow saying something about the variability of that estimator to give, a confidence interval on the estimate. But there are a few downsides here, which is that we do not necessarily return an interval with known physical constraints. And again, some mathematical detail here will reveal that the length of this interval is very dependent on the conditioning number of this particular Gram matrix, which is the linearized version of our forward model. And it turns out that this two-step procedure makes these intervals very sensitive to both noise and the true parameter setting, which we'll see in the empirical results here in a second. Okay, so to the empirical results, again, we're looking at interfacial stiffness intervals, and we're going to look at coverage and expected length properties of this method in a simulated version of our application. And we'll explore these two different parameter settings, and since unknown variance is key, we'll look at our method performance across a variety of noise levels and see some interesting results. So again, we're looking at these two parameter settings. Okay. In the typical setting, we see that our SSB method outperforms, I'll suggest, with higher noise. Now you might be saying, well, but it overcovers. We're looking at 95% intervals here, and on the left you can see that our intervals are basically nearly always covering across all noise levels. Interestingly, though, the least squares intervals start to underperform in terms of coverage at the higher noise levels, which can maybe be explained by the fact that they start to blow up in terms of expected length at higher noise levels. And again, this is a mathematical result stemming from the high condition number of that matrix that's involved in the standard error. So interesting phenomenon here, actually, I'll just say in passing, that you can have worse coverage and longer intervals. So this can happen sometimes. Okay, and kind of the other interesting and key setting here is this boundary setting. You can see that our intervals are still achieving the desired level of coverage, and we can see here that we're getting bamboozled across the board for our least squares intervals at all noise levels in this boundary setting, which I'll say again is because of this one parameter being on the known boundary of the constraints. Okay, and I think I got myself back on track here. So just to recap and provide some next steps, I introduce a UQ method for bonding composite non-destructive evaluation, and we provided confidence intervals with coverage guarantee. This required extending some existing optimization-based interval methods by developing ways to handle unknown variance, nonlinear forward models, and interval propagation. And some of these empirical studies show that our SSB method outperforms the baseline least squares method in high noise settings and in kind of this adversarial nuisance parameter setting. And just some next steps here. The first is I'm actively working with Peter Spaeth, whose name I forgot to mention. He's one of our collaborators here, to provide rigorous proof that our two-step procedure actually does provide this coverage guarantee. I've also been exploring generalization of the Gaussian noise assumption. There's actually some interesting, I'll put distribution free in quotes, approaches to this, which allows us to just work with symmetric noise distributions. And of course, we're waiting on some real data to be generated so we can actually deploy this thing with some non-simulated data. And with that, I'd like to thank you for your attention. Please feel free to reach out to me if you'd like to connect, and I'm happy to take some questions if we have time.
So if you have a question here in the room, please go to the mic over there and ask your question. Any questions from the room?
Hello, great talk. Question: When you say confidence interval, is that confidence interval on the mean of the parameters, or what is a confidence interval over?
So that is a confidence interval on the true unknown parameter setting. So the parameter here I'm talking about is a value. Oh, the screen doesn't like your question. So the parameter here is an actual parameter that goes into the computational forward model. So of course, if you observe some data and you're trying to make an inference about that, that's the uncertainty that we're trying to characterize here. So yeah, I guess it's a little bit of a different way to think about confidence interval from maybe traditional statistics literature, where you're trying to estimate a mean or some moment of a distribution, something like that.
Could you highlight that more about what would that look like if you did a tolerance interval on this? Could you? I'm trying to understand how does that differentiate from other statistical intervals that I do know?
Okay, that's a really good question. I'm only vaguely aware of how tolerance intervals work, so I unfortunately can't maybe comment on that specifically. But the way I think about this is, I want my procedure to give me a set that if I do this procedure, a million times, and I have some way to test if my interfacial stiffness value is within that set, that at least 95% of the time, for instance, that true parameter setting is within that interval. And that should be true regardless of what that true theta star is. So there's some ways to think about this in like a decision theoretic sense. This is kind of like a min-max way to think about developing a statistical procedure. I'm not sure if that helps.
A little bit, but I guess I have one more question if you have time. What is that parameter length? Could you explain what that actually meant?
The parameter length. Can you?
Is it possible to go back a couple of slides?
Yeah.
Expected length. Sorry, expected length. Yeah.
Okay. So what this is I've simulated. I think I did 2,000 simulations, and so this is for the typical setting. So for each of those, I use my procedure to construct the intervals. So that's just solving those endpoint optimizations. And then to get the length of that particular realization, I just look at the length of the interval. I do that 2,000 times. I get 2,000 lengths. I average them, and that's a point on that. That's a point on that plot.
Okay, thank you.